Good morning students. In this video I would like to explain one of the shift register, that is SIPO, serial in parallel out. We know that there are four shift registers. First one is serial in serial out, SISO. Second one is serial in parallel out, SIPO. Third one is parallel in parallel out, PIPO. And fourth one is parallel in serial out. Okay. Coming to serial in parallel out. Single input, but parallelly we are taking the output. So there is only one input, but shifting data is taking place, and we are taking parallelly data out. So every clock cycle we are going to have parallel data out. Say for example, if you fill QA, QB, QC, QD with initial values, then only we can have QA, QB, QC, QD, and they'll be shifted. But if you have not loaded any predefined values, what happens is during first clock cycle you can see QA as D in, whereas you don't know anything for QD, QC, QB, QC, QD. So we are going to have an undefined state. If you don't preset or clear to set the initial values for all these four flip-flops, so what it will give you, it will result an undefined state. And depending on the shifting, depending on number of clock cycles, the data will be shifted, and accordingly you can see the data. Okay, that is about SISO. SIPO, we'll see the execution now. Yes, we are having a single input, that is serial in over here. So SER IN is the input bit, and we require a clock, that is also an input bit, but we are parallelly taking the out at every interval of the time. So P out is output, and that I have called as array, that I have taken as array. So P out of 3, P out of 2, P out of 1, P out of 0 are my outputs. Under architecture, I have called a signal. I have declared a signal temp, which is also of size 3 down to 0. So TMP is my element using which I am making all the process, and finally I'm going to send the temp data to P out. So it can be processed this way. Okay. After signal declaration, it is begin in process of clock. Then begin if rising edge of the clock, or we also give this way, clock tick event and clock is equal to 1. So during this interval of time, then what our intention is? Our intention is to shift the data serially and collect the information. Collect the information parallelly. So what it is happening is, so what you're doing, this is of MSB, so 3, 2, 1, 0. I have taken them as P out. So P out of 0, P out of 1, P out of 2, and P out of 3. So what is happening is you are going to append D in data input, that is here we have named it as SERIN. So SERIN, so serial input enters, and this data is shifted. So then now we are using temporary variable. Okay, so this TMP of 0 goes to TMP of 1, and then this TMP of 1 goes to 2, and 2 to 3 along with serial input data. That is what we are showing over here. So I'm not sure, I have not taken the bits over here. Say for example, if your array is temp 3 down to 0, see, you have declared temp 3 down to 0. So here I have taken, it is again as a syntax, but for our understanding I have taken. So it is temp 3 down to 0. Okay. At temp 3, temp 2 bit comes, and for temp 2, let me fill this also, 2, 1, 0. So now there are going to be 4 bits, temp 3, temp 1, so temp 2, temp 1, temp 0, and here also 4 bits, temp 2, temp 1, temp 0, and serial in. So this temp 2 will be come to temp 3 position, then 1 goes to 2 position, 0 goes to 1 position, and serial in data comes to this 0th position. That is what is this AND. It is a concatenation operator that we are using here. We are using the symbol over here. It is a concatenation operator. So temp 3 down to 0 is now filled with the data 2 down to 0 and serial input data. And finally this temp is given to P out. This is what is the test bench. Please go to the test bench. So here I have simply taken this clock statement. Okay, one more point that I would like to show you here is I would like you to see the technology schematic. See, we have nowhere we have called 4 registers, but we have taken array of 4 bits. See, we have taken output as 4 bits and we are processing this way. But here physically the 4 registers have come into the picture. That is the beauty of these reconfigurable designs. See, in the program nowhere we have shown that we require 4 registers. See, serial input data, clock and P out. We have not called D flip-flop or any of the flip-flops. But if you see its technology schematic, this is how it looks. Okay, this is how it looks. See, this is MSB bit, and then the second parallel output data that comes over here, and then this line is taken over here, and then this is the LSB line that is over here. That is what is P out 3 down to 0. Please verify this. We have nowhere given that we require 4 flip-flops. But this software, what it has done is it understands our requirement and it has created our technology schematic this way. See, it is internally using a D flip-flop. Please check the program. Do I call anywhere D flip-flop? No. But the technology schematic is showing a D flip-flop internally. It is a buffer ma. Whenever you require a buffer, it takes the help of D flip-flop. Yes. After that, this is what is the test bench. Let me move to the simulation window. Yes, simulation. Click on it and double click on the simulation behavior, simulate behavior option. Then it gets simulated. And one more point that you have to observe here is we have not given any initial value to the P out. We have not given any initial condition. So what happens is, see, I made my serial input data is equal to 0 and every 25 nanoseconds the clock is on and off. But at every rising edge of the clock there must be change at my output. So first what happened is my input is equal to 0, it is serial in parallel out. So serial input data enters into the LSB flip-flop, that is P out 0 gets the output during first clock cycle. Before that is the undefined state, and then during the next clock cycle, during second clock cycle, this P out of 0 or temp of 0 will come to the second flip-flop. Okay, the undefined state over here at QB, it will be processed by the third flip-flop, so it is still undefined state. Okay, and previously QC is also at undefined state. Then my fourth flip-flop, that also process the undefined state. So during second clock cycle, these two are at undefined states, whereas whatever is the Q in, whatever may be the QA, that will be processed by the second flip-flop, and so on. So if you see, during second clock cycle, P out of 1 is equal to 0. Then during third clock cycle, P out of 2 has got the output as 0. Then during fourth clock cycle, P out of 3 is equal to 0. And we have not changed our serial input data, so it has come like this. So after say 200 nanoseconds, I'm going to give my serial data as SERIN, serial input data, as 1, and we'll verify. Expecting semicolon, yeah. Yes, see, I made my serial input data and it waits after 200 nanoseconds. So here we have seen the explanation till this part, and from next clock cycle, I made my serial in data is equal to 1 during the falling edge. So during falling edge it won't respond. Coming to the next clock, next rising edge of the clock, whatever the value of the serial in, that enters into P out. Next clock cycle it shifts and it accepts the serial in data into this, and so on. This is how it looks. Please verify the waveform, and I'm going to make the modification. What I'm going to do is copy, paste. After 50 nanoseconds, I'm going to give my serial data as 0. Save. Execute. See, we made serial in is equal to 0 till 4 clock cycles. So your 4 flip-flops are filled with 0 0 0 0. It got shifted, and then we gave this serial in data is equal to 1 during only 1 clock cycle. Okay, and then after it is equal to 0. So this 1 you can see this way. So now it is 1 all zeros. So it first it during the next positive edge of the clock, serial in data enters into P out, and next clock cycle serial in data is again updated by Q of 0, whereas this Q of 0 is taken to the next level, to the next flip-flop during next clock cycle, and this Q of B will be propagated to Q of QC, and then QC to QD, and so on. Okay,